So if you write phi j transpose times the mass matrix times bi, this will become 0, and this is 0 value non-matrix. So here we can write down what we call model orthogonality in this mathematical form, which is written this way. This operation when I and j are the same, this operation will not give you 0, but will give you either modal mass or modal damping or modal stiffness. But when I and j are not the same, we're going to get 0. In other words, if I can subject the whole thing with a certain mode to the entire governing equation right here, which is this one here, then I will take just that mode out of the equation. If I subject the whole thing with the ice mode, suppose I only do this. Suppose, and if I do it to the left-hand side of the equation, you have to do it to the right-hand side of the equation. And keep in mind that in matrix or vector operations, the order matters. Multiplying of a matrix term with a vector or a matrix in front of it will give you totally different results as if you operate for this one.
Professor,
Yeah.
I think there's someone who's trying to log in, but it needs your access.
All right. Okay. Thank you for your reminder. Right? So this model orthogonality will give us one very important and unique result, which is because the dynamic displacement is simply just the superposition of mode-shaped vectors in generalized coordinates. And no matter you differentiate with respect to time once or twice, it does not change the mode-shaped vector. Did you notice that? Because for dynamic displacement, it has the mode-shaped vector in it, right? If you differentiate it again, this time derivative will only apply to generalized coordinate, will not touch the mode-shaped vector, correct? So it's the same in velocity vector, the same in acceleration vector. The mode-shaped vector always remains untouched. And this is the beauty in the modal orthogonality, because in here, in this dynamic, well, in this acceleration vector, it also has a motion vector, untouched. It's the same motion vector as the one in velocity, as the one in displacement, correct? Can you see that? Expression here. All right, I think I can use red, weaken back, just to show you where it is. For displacement, it carries one component of the motion vector. For velocity, the same thing here. For acceleration, the same thing here. And these are the same. They are the same and the very motion vectors. They don't change. Which is why when you carry out to here, you can just use the modal orthogonality to remove all other modes by keeping only that certain mode out. So the regional governing equation then can be written as the assembly of individual modes. Because if I apply the first mode to this governing equation, I will only keep the first mode out of this governing equation. And everything else will be 0 because of the modal orthogonality. Modal orthogonality says very clearly, if you subject any kind of motion vectors to the governing equation, to whatever your displacement, velocity, acceleration, only when the numbers are the same. That means you pick the first mode, it will only keep the first mode out of these results. Every others, if it's not the first mode, it will be 0 because of when I is not equal to j, the result is 0. So model orthogonality give us very, very useful result. And here, originally, we are dealing with vectors and also matrices. And this kind of math is not easy to solve. But after this model orthogonality, we can write it like this. We can write all these. We can write this to become this. If you apply the first mode, let's say phi1, you apply the phi1, and eventually you're going to get only the phi1. So this will become, you will keep this one here, and when you apply the subject this one to here, you will only have z function of t double dot plus v1 transpose times, well, actually this will be ci times z dot. So the z double dot vector means not just for the first element, but for all of them. So I don't have the subscript here because the subscript is putting the vector. Notice the difference between these two. Plus k, of course, this will become c1, become k1, and this will become c1 over m1, c2 over m1 times z as a vector of t equals, this will become p1 over m1. So if we operate the first mode, we're going to get this result. If you operate the second mode shape vector, v2, to the original governing equation, the original governing equation is an n by n, big chunk of matrix. If you multiply everything by the transpose of the second mode shape vector, you're going to get the second mode, which is, so this one is only for the first mode. And the second one is also, of course, z of t. So you may want to say this is 1, this is 2, this is 2, because only for the second mode, plus c2 over m2, z2 of t, plus k2 over m2 times z2 of t equals p2 over m2. And so on and so forth. The nth mode will give you Zn double dot. That's the generalized, well, the second order time derivative of the nth mode plus Cn over Mn times Zn dot times T plus Kn over Mn times Zn of T equals Pn over Mn. Now, by using modal orthogonality, the original whole big chunk of the matrix, n by n matrix, can be decomposed into this. So the power of this definition goes all the way to the very core of simplifying the n by n governing equation becomes the n set of single degree of freedom systems. Because in each one of them, you have just one, you no longer have matrix. It becomes C1 over M1, and C1 is a number, M1 is a number. So this will become just a number. Therefore, the original n by n matrix problem now has become each one of them are all single degree of freedom system. Now, if they are single degree of freedom system, you know how to use the solution from what we talk about in February.
Professor, someone is trying to enter the classroom.
Okay. All right. All right, thank you.